Hi everyone. Today we're going to be talking about conductors and insulators. These are materials which allow the flow of electricity and do not allow the flow of electricity respectively. It turns out that not all conductors are metals, so we'll be looking at some of the more interesting sorts of conductors. Now, in materials like metals, the charge carriers, which are electrons in the case of metals, are free to move around quite easily. So we have charge carriers that are easy to move, that can very easily transmit electric charge and electric current. If we apply even a small voltage, even something in the region of, 1,000th of a millivolt, then the electrons will quite happily move across and produce an electric current because they're free to move. So we call a material like this a conductor. In a conductor, we have plenty of charge carriers that can move around even with low voltages. Other materials might have very few charge carriers, or they might have charge carriers that are locked in place. An example of a material like this is a block of wood. If we apply a very large voltage, then we won't get any charge carriers moving, and we won't get any current flowing. We call a material like this an insulator. You can see that when you connect an insulator in circuit, you won't get the light bulb lighting up. Now, if the voltage across a conductor is small enough, then we won't really be able to notice the current very well. And on the opposite hand, if we have a voltage across an insulator that's extremely high, then we might be able to cause current to flow, which is why lightning is able to strike trees. So current flowing through a tree will occur when lightning strikes it, even though the tree is made of wood, which is an insulator. Makes sense, right? So if we have an extremely small current, we might not notice that something is a conductor, and if we have an extremely high voltage, we might not notice that something is a resistor. Now, in general, metals make better conductors than other materials. So the best sort of conductor is metal, whether that's, iron or copper or aluminium or mercury. Graphite, which is a little like charcoal, is an example of a non-metal conductor. Can you remember what graphite is made out of? It's made out of carbon. And salts and strong acids can also make good conductors as long as they're dissolved in water. So graphite and salts and strong acids are all examples of things that are conductive even though they are not made out of metal. Now, when we have salty water or acid water conducting electricity, it's important to remember that the conductivity of the liquid is due to the dissolved salts or the dissolved strong acids. Pure water is not very conductive at all, although it's not as good an insulator as some other materials. Now, to conduct electricity, a material has charge carriers that can move, otherwise it can't have an electric current flowing through it. The outer electrons of metal atoms are free to move through the metal. We learned before that the electrons are moving about at random, even if there's no current flowing through the metal. So the electrons are able to carry charge around in the metal very easily, and metals make good conductors. The electrons of an insulator, on the other hand, are bound tightly to their parent atoms. They really don't want to move. So unless you apply an extremely high voltage, they're not going to. So they are not free to move and cannot carry charge around the material. And this means that insulators can't conduct an electric current. Now, let's look at some conductive liquids. Pure liquids consist of neutral molecules with tightly bound electrons. Initially, this makes it seem like they're not very good conductors of electricity, except of course for mercury, which is a metal. But when a salt or an acid dissolves in water, the salt or the acid will separate into ions. If we dissolve sodium chloride, table salt, in water, it'll separate into sodium ions and chloride ions. If we choose an atom instead, one of the ions will be a set of hydrogen ions, and the other ion will be specific to the acid that we're using. So an ion is simply an atom or a set of atoms that has an electric charge. In the case of table salt, the sodium ion has a positive charge and the chloride ion has a negative charge. This means that if we take salt as a whole, equal parts sodium and chloride, it's negatively neutral. So the solute, that is, the thing that we dissolve, separates into positive ions and negative ions. assuming that it was uncharged in the first place. So both types of ion are freely able to move through the water, right? And this means that they can act as charge carriers. We can see in this photograph over here that we have a container filled with blue liquid that is conducting electricity. So both types of ion, the positive ions and the negative ions, are able to carry charge through the liquid and allow the solution, that is, the dissolved stuff in water, to conduct electricity. Let's look at gases next. Now, gases are made out of neutral molecules, much like liquids. And unlike liquids, there is no such thing as a gaseous metal, at least at room temperature. Anyway, the neutral molecules are insulators because they don't have electric charge, right? But when gases are heated to extremely high temperatures, that is the thousands of degrees Celsius, or if they're subjected to a very strong electric field, thousands of volts, then they will ionize. So knowing what ions mean, what do you suppose ionizing is? Well, it means the gas molecules and their electrons are separated, right? So instead of being neutral gas molecules, they become charged gas molecules, that is ions, and electrons. They've been driven away by either the high electric field or the heat. Now, if we have ionized gas, we have another name for it. We often call it plasma. Now, in a plasma, both the electrons and the positively charged gas ions are free to move. Gas is able to move across pretty freely, so if we remove the electrons from them, it won't change their behavior much, but it will mean that the ions are now charged. The electrons, of course, are free to do as they please once they're free from their atoms. So because the positively charged ions and the negatively charged electrons are free to move around, both of them can act as charge carriers, which means that a plasma is able to conduct electricity. And this is in fact what lightning bolts are made out of. So that's the end of the theory. We've learned about some of the various different types of material that can conduct electric charge. Let's go on to some questions.